Hey Rick.
Hey there. How's it going, Alex?
Oh, I'm good, thank you. How are you?
Doing well. It's been a bit
It has been a
since we've
bit.
been on a Zoom call. Yeah.
Yep. Morning, Jing.
Morning. Hi, Alex, Rick.
Um, are is Grant going to be joining us as well?
Yes.
Okay, cool. Where are you based, Rick?
I'm in Austin, Texas.
Ah,
Where are you at nowadays?
I'm in the UK.
You still over there?
Yeah.
How's the summer been so far? Has it been very hot or
No, very mild actually.
it's been kind of mild here. It's wet. It's wetter, much wetter than usual here.
Oh wow. Okay.
Yeah. Yeah, for the first time we're like out of a drought. It rained yesterday. I can't remember the last time it rained in mid-June in Austin. It's been more than 10 years. Yeah.
I'm still traumatized by the snow blizzard we had in Austin when KubeCon was there a few years back in the middle of November or October even.
Ice ice apocalypse.
Yeah.
Yeah.
Um, we might want to wait maybe just one more minute to see if a few other people might join. But the call is being recorded for later as well.
Great. How many people usually end up on the call?
Um, I don't know, maybe 10 or so.
Great.
Why don't we get started?
Okay. I will uh let Grant do the presentation. Do you have to give share privileges? I guess everybody can. Okay. And then both Grant and I will kind of co-present here.
Cool. Would you be able to share the presentation afterwards, or is just
Yes,
Oh
definitely.
yeah, yeah, absolutely.
Yeah.
cool?
Hey, good morning, everybody.
All right. So I guess to get started, we'll introduce just a little bit about us, so everybody knows who we are if you haven't met us before. My name is Rick Vasquez. I live in Austin, Texas, and I've got my colleague Grant Mackey here with me. Um, we have a company called Jackrabbit Labs, where we focus on unified memory fabrics platform. Now that sounds really big. What we're here to talk about today is mainly CXL, and we'll give a brief introduction to what CXL is and why that's relevant and why we think that's relevant to kind of CNCF in this landscape. But from a broad overview perspective, we believe the next era of compute that's going to be driven more by AI inferencing and some of the use cases that we're seeing kind of come up and bubble up right now is just getting started. And a key enabler of this next era of compute is going to be a shift away from the primary mode of storage being persistent storage and moving more into memory and persistent memory being that first class citizen that's being leveraged all over the place. And because of that, um, large memory pools are going to be needed, and then the sharing of that memory between discrete systems outside of single system boundaries is going to become very important. So with that, I guess we can talk a little bit about CXL and how we got here and the memory problem.
Right.
So this is just some background, right? CXL is not a fad anymore, right? Back about 10 years ago, we had sort of a the open standards duke out. You had the C6 effort in the ARM community. You had CAPI and OpenCAPI in the Power IBM community. You had Gen Z, which was an HPE thing, which was ambitious and had trouble getting traction in other places. Intel threw its hat in 2019 with Compute Express Link, and they finally said, "Fine, we'll open up a path to the coherency bus on our cores because apparently we need to, right?" For a few more years, they fought out, and everybody sort of relinquished and rolled their IP into the CXL consortium. That's the primary takeaway. Other takeaways are that the CXL community moved aggressively with their standards, and they kind of pumped out a bunch of versions, kind of like bang, bang, bang. And everyone was like, okay, that's a lot of documentation and nothing in the market to use it. So it's a cool story, bro. So at this point, we're on a 3.1 spec, and we don't yet have 2.0 hardware, which is one of the things I think we'll talk about later in the presentation. But we are getting there, right?
Yeah.
The next generation Intel platform will have 2.0 support, and the follow-on generation will have 3.1 support. So like,
And we'll
it is
get
catching
into
up.
yeah, we'll get
What that
into
means.
what that means and what types of devices are here on CXL. I think the important thing to stress here is CXL is one of now many that have been announced memory fabrics, and that's why we talked about unified memory fabrics. Right now, we are very focused on CXL. It actually has a specification. There is hardware shipping, and it has been essentially the work of the past 10 years between lots of very large silicon vendors and device manufacturers to get to the point where we are to have a mature specification that's well defined and has a real product roadmap with actual silicon being taped out and FPGAs supporting the possibility of memory coherence. That's a provable thing at this point instead of just a figment of everybody's imagination or something that we're wishing and hoping for. Now, one thing that is pretty obvious at this point is we look at this list and it's a bit light on software, right? So we have lots of accelerators, lots of CPUs, lots of memory controllers, ASICs, all kinds of testing frameworks, appliance vendors, intellectual property that's being developed. But really from a focus area and a key enablement piece of technology is the software. And we see what NVIDIA has been able to do with things like CUDA, Nickel, and Doka to enable their hardware ecosystem. And that's a really big reason why they're able to have the adoption rate that they have now is, well, you know, whenever you want to put NVLink and strap a bunch of GPUs together and then strap a bunch of memory together with a bunch of ARM cores, you can do that with Doka, Nickel, and CUDA to be able to do that. And so what we're seeing now, especially in the last month or so, with the announcement of UA Link from AMD, Intel, Broadcom, Cisco, and others, is that, you know, there's a true appetite to do this out in the open. CXL is essentially that CPU to CPU or CPU to XPU type of connection. And then UA Link serves as that GPU to GPU type connection. And then Ultra Ethernet which we're not really going to talk about today, kind of is beyond that and goes more interconnect to interconnect.
Yeah, more rack to rack kind of cluster configuration, right? Okay, I think we talked about this, right? It's the CXL consortium. They have a cadence, right? The spec is progressing forward as they feel it needs to. This is a really nice link down at the bottom. It has basically everything, all their trainings, etc. Right? If you're unfamiliar, like we'll go over this just for folks that may be unfamiliar with the devices, right? But if you are familiar with the devices, we can skip this bit. So
I think this would be useful to go through.
okay. So things that have existed in the CXL spec for a while are this idea of typed devices, right? So this has been a thing since the CXL 1.1 spec, and they're starting to migrate away from this delineation of device types, but it still holds. Very appropriately named type 1, type 2, type 3. Type 1 devices, okay, so first off, CXL is a memory coherency fabric, right? Plain and simple. It's sort of moved into like the more focused on CPU to CPU and CPU to accelerator with the onset of UA link and Ultra Ethernet sort of throwing its head in as well. But it's like cache coherency protocol, right? So type 1 devices are a memoryless cache device, meaning that this is good for accelerators with a mailbox. This is good for PGAS NICs, where PGAS is parallel global address space. So like putting a memory array across a set of machines and then doing pointer chasing across machines, right? Stuff that's close to the CPU, basically. Type 2 devices are coherent memory devices. So they have the functionality of a type 1 device, but then they also have a DRAM pool or a memory pool, load store addressable pool associated with that cache. So this is pools of shared memory. This is just coherent far memory and GPUs, right? GPUs would classify, but sort of moving into UA link for GPUs. So still counts, but maybe not in practice, right? And then type 3 devices are just more memory. I just want to hawk in an E3S or connect some stuff to the fabric and then give the CPU suddenly like 3 more terabytes of DRAM. And the coherency interface on the CPU complex has to make sure that it's correct, but this is just like an extension of space. And those are the primary designators, right?
And I guess at this point, we have kind of glossed over CXL at this point sits on top of the PCI Express interconnect. So CXL is not tightly coupled with PCI Express as its exclusive interconnect. Right now, it's the only implementation that exists. So the way that you do CXL is through PCI Express, and then you have a CXL link negotiation that happens to use that PCI Express underneath.
Yeah.
Okay.
So I mean, they are
Can I just clarify a little bit here?
absolutely.
Sure.
Yeah.
So with type 2, you say we have coherency, but with type 3 we don't have coherency. So type 2 is kind of for use cases where you have a workload running on multiple nodes, but it's sharing the same memory. But type
That's right.
3, okay, cool. And then type 3 presumably be where you want to kind of like almost disaggregate the memory from the compute and allocate it dynamically over the fabric.
Correct. Yeah. So with a type 2 device, you have the coherency engine lives on the device. So like the device is responsible for going out to the other sources of coherence and being like, do I actually have exclusive access to this, right? Whereas a type 3 device is just more DRAM as an example. And then if you needed coherency on that large pool of memory, you would have to do it in software, or you wrote like this amazing code that no one believes, and it just happens to Yeah.
Yeah.
If it was like a read-only space, right? Like if it was a load-only pool, you could expose a bunch of hosts to it and it would be fine because it's a read-only cache. Something like that would be fine, but the second you modify anything, another host would be like, I thought I was the sole universe and now this data has changed. I'm going to explode. That would be your experience with a type 3
Yeah.
device. Yeah. And so, yeah, the other thing, PCIe and CXL are orthogonal, right? Like one of the things that you'll see on there is that so long as the PCIe bus is Gen 3 or later, this will work. If you plug in a CXL device and there's a CXL IP on the other end, the link negotiation can go all the way down to 3 because you just need the PCIe bus to support TLP, right? It just needs to be transaction, um, because 2 and 1 don't do that, right? But this is a little nitty gritty. But with Gen 5, there's 2 sources of communication in CXL that are 68 byte flits. And then there's a third one that's the traditional 4K PCIe packet, well, message. And then when PCIe goes to Gen 6, everything will become 256-bit flits. And then CXL and PCIe traffic will pretty much be indistinguishable, except for a few bits that distinguish it as a CXL message rather than a PCIe message. So they're very tightly coupled, but CXL is pretty much just a communication protocol. It doesn't rely on PCIe. It's just they go together well.
Yeah, and I think if you go to
it's a
the next
nuance.
slide,
Yeah.
you can kind of show some of that. Yep.
But in
Yeah.
terms of like practicality purposes, we're kind of like extending the PCI bus across servers.
You can use the PCI bus to now have cache coherency between things that are not within the server.
Okay.
Or add expansion within the server, leveraging like memory. So I guess the 2 ways to think about it. One is system to system. And that's something that's new to PCI Express, where PCI Express is mainly for peripherals for a single system. CXL enables that beyond the scope of a single system. And then within a single system, CXL also has benefits other than PCI Express. You can't put a DRAM device into a PCI Express bus, but with CXL, you can add DRAM and have that be addressable by the CPU as DRAM into a PCI Express port. So you can think of it as the transport layer is what it's leveraging PCI Express for, but not any of the underlying standards outside of transport.
Right, but it operates at sort of PCI speeds, not DRAM speeds.
Correct. The bandwidth and latencies are PCI Express. They're limited by the underlying interconnect. Yeah.
Yeah. They're limited by whatever the transport is. Yeah. So this is an eye chart. I think the only thing I really want you to get out of this is that there are more features on the right. 1.1 was really getting your feet wet. It's just basically it exists and there are devices. 2.0 is where you start to add one layer of CXL switches allowed, and you get some data integrity and encryption on the links. You can do pooling. Basically, like 2.0 is where CXL starts to get interesting, but then 3.0 and 3.1 are where it's like mature, right? And that's pretty much what you take away from this.
Of 2.0 to be very similar to the world that we have with something like NVMe over fabrics, but with actual DRAM and memory. So you can have a single switch topology that has a significant amount of DRAM resources attached to it that can be routed to multiple systems that are hooked up to that single switch.
Yeah. Yeah.
Okay.
3 dot, so you might be like, okay, well, 3.0 and 3.1 are very similar, except for that last square. And that is correct. 3.1 was, we spoke briefly about Gen Z. 3.1 is where the Gen Z consortium really sort of asserted themselves into the specification. Up until 3.1, everything is very much loads and stores and hierarchical, right? Like everything is sort of dependent upon a host or collection of hosts, and it's not a bidirectional communication, right? It's one way, right? Whoever is the source of coherency is kind of the boss. With 3.1, you add another 280 pages to the spec, and it's all the port-based routing stuff. So with 3.0, you're allowed to have multiple switches, and more importantly, hierarchical switches. And then 3.1 is like, rather than root ports and memory addresses, let's have actual ports, right? And whether or not that will work in practice will remain to be seen, but that's sort of the largest differentiator between 3.0 and 3.1 is that it starts to look like a network rather than a collection of devices and a memory space. So it's a big difference. Yeah.
So just to make sure I'm understanding this and kind of summarize it, with with CXL 2, you have a bunch of nodes connected with a switch. With CXL 3, you have a bunch of switches and a hierarchy of switches. And with CXL 3, but it's a flat fabric. And with CXL 3.1, it's not a flat fabric anymore, and you can have routing decisions.
Correct. Yeah.
Which has obvious implications. It seems like a simple change, but it's fairly drastic. It wasn't enough to increment it to 4, but it it changes things rather drastically.
That minor
Right.
version was quite large. Yeah.
Yeah.
I think that's the takeaway, was that minor rev was huge. So yeah, I mean it's one of those things where peer-to-peer communication gets added in 3. So that's why I still sort of say like CXL is still sort of proof of life, right? Is that you can add one switch and you can have multiple hosts on that switch and you can have multiple devices on that switch, but the hosts still can't really talk to each other. But then in a 3.0 situation, you can still have just the one switch, but now the hosts can see each other and you can have shared memory pools and they can do all the really interesting things that a coherent memory fabric can do. And then 3.1, it's, you can have hierarchical switching and somehow violate the laws of physics to have multiple hops still be under 300 nanoseconds. But we'll get there, right?
Yeah, I mean, I guess the difference between 2.0 and 3.0 is in 2.0, you can have essentially volumes that are attachable to anything that's on the switch topology. And then in 3.0 and 3.1, you can have any number of writers to that same shared block device. And because of that cache coherency, they're not going to clobber. So they'll be able to. I don't know that there really is something that is multi-writer on single block device that exists in the storage space, but that would be something that we're talking about semantically in 3.0 and 3.1.
Right. Okay.
Yep.
So, like I said, it's an eye chart, but it's a good summary of just showing that like as you move forward, it gets much more feature rich over time. Okay, so this is us. This is something that we have open sourced, and we've got a YouTube video. We talk about it, stuff like that. That's where this goes. Can you see my mouse?
Yes.
Okay, yeah. So this QR code will take you there. At the CXL DEF CON this year, we got a shout out to our fabric manager. So one of the things that you get added in 2.0 is a collection of API calls that allow you to check the health of devices, set up virtual CXL switches, which is basically like a VLAN for the CXL switch to, glom a few physical ports together under a port complex to provide a collection of resources for the host. A few other things in it, and basically it's a collection of calls. So they call it a fabric manager, but really it's just a fabric API, right? It's just a way to do stuff, but there's no layer on top of that that says, okay, well, I need to express a need, right? There's no need expressing, it's purely functions. So we wrote something on top of that we've been calling an orchestrator, wherein a user can say, I need you to complete this action, which is a set of steps. And you get useful output from the fabric so that the host can do the things it needs to do, right? So to implement that, we talked about how like hardware isn't really available. So the QEMU framework has done a lot of work trying to emulate these devices as best as possible so that they can test driver stack code and stuff like that. Jonathan Cameron and some of the folks in that community have done a good job trying to emulate CXL switches. It needed a bit more, so we wrote an emulator which sort of wraps around what abstraction exists in QEMU now so that you can test FMAPI calls and test configurations so that higher level software stacks can kind of just plug in when these things do exist, right? So that's the CXL switch emulator. And then we wrote Jack, which is just another CLI orchestrator, so that there's a terminal wrapper around this orchestration this orchestration layer. The idea is that something like Kubernetes would use what Jack is calling, and they would be able to express need to the fabric to expose devices and pools and stuff like that. So that's this slide. It's all open source.
Can you show a link of that GitHub repo? I can't see.
Yes, I can put it in the chat for us.
All right, thank you.
Yeah, absolutely. And then we'll make sure to get this presentation out, and this is an active link. This will take you there too. But yeah, so that's really all we have here. This is moving forward. This is fully 2.0 compliant, and we're working towards 3.0 and 3.1 compliance so that all of the FMAPI commands are encapsulated and so on and so forth.
So yeah, I guess now we get into, well, what does this all mean, and why are we talking to CNCF, and how does this fit into the Kubernetes landscape? Obviously, it's pretty exciting to have new hardware profiles and memory pools and shared memory, but how does that kind of fit into the story with where we are with cloud native computing? Well, right now, I think everybody, it's meant to to show kind of some of the absurdity that we have with the microservices architecture. But we all see this, like there's complexity inherent to these very large systems that we're deploying with microservices. And each one of those microservices needs to talk to other microservices or those data sources. And I think everybody here understands and knows this problem really well. One thing that we see with the advent of these microservices and with deployability being much higher in a managed setting in Kubernetes is we have a lot more replicas and copies of data, especially whenever we're talking about persistent data systems or databases, where we have replicas that help achieve either read scaling or sharding with write scaling. And those were ways that we were tackling problems because we had either discrete system boundaries where we couldn't vertically scale a system large enough to handle the entire database, or because we wanted to split that database up into smaller pieces so that they can sit closer to the microservices that leverage them. And then we can pay the penalty later whenever we put all of those back together in something like a data warehouse or a data lakehouse, where that penalty is relatively cheap to the end use case of those analytics engines that don't necessarily need that data in real time or near real time. And then you have real-time streaming data sets that are living in memory and persisting some that are passing data in event-driven architectures between services. So that is what we're trying to represent on the left, which is probably, to this group a very known problem. And then on the right, what we talk about with shared memory fabrics and kind of coherency across these is, imagine if you had a pod that can be scheduled on any worker node, and then that pod could have some DRAM attached to it, or all of the DRAM attached to it actually be shared with any other pod in the cluster. And so now, if you're talking about database systems specifically, if you are wanting to do synchronous database replication, instead of doing logical replication, or depending on the block layer to do block level replication and then acting through the application interface, you actually just have one memory pool that's shared between multiple containers, and then those can flush their persistence to their own independent disks in different fault tolerant failure domains. So instead of having, yeah, sorry
Hey,
about
sorry
that.
to interrupt. I'm not sure I fully understand the concept here. So
Okay.
you're saying you have multiple pods on different nodes sharing the same coherent memory. So
Mhm.
this isn't like sort of the type 3 thing, it's more like the type 2 thing.
Yeah. So I
Right.
guess we
Yeah.
can step through. Yeah, we can step
Like
through
this
how we
is
get there.
pictures,
That's the
right?
Yeah, I guess the eventuality is, okay, that's where we get. The first step, though, and something that's still extremely valuable to the Kubernetes community and basically all cloud native deployments, is I have a worker node that has run out of memory but still has CPU to allocate or provision, and now I can attach more memory to that worker node instead of having to reschedule pods from other nodes all around to play the Tetris, right? To do what Kubernetes does best. Now I can actually just grow a little bit dynamically, as long as I have MCPU and a pool of DRAM that's addressable by the entire cluster instead of each individual worker node.
Okay.
And so that's the pooled memory section there.
The pool memory or the memory expansion?
Memory
Data,
expansion is
so
just
yeah.
single system. So that would be, I have a worker node, and this worker node, for whatever reason, we just know we're going to use lots of memory on. I can plug in a DRAM device without shutting down the worker node and actually expand the DRAM capabilities of that worker node with a device. With pooled memory, you don't have to do that to the specific system. You can actually just have that as long as the system is plugged into the CXL switch.
Yeah, this is, I
Then
mean, this
then
is
it
the sort of like today 1.1, 2.0, 3.1, and so on and so forth. This sort of the flow of this diagram, right? So this is just giving your box another 2 terabytes of DRAM on top of, local DDR DRAM. And then this is an instance where, like, I have a container, I have a pod that's about to fail with an and I can give it a bit more. And then on the opposite direction, this is something that we've discussed with Uber, is that they actually, in some instances, they have a core stranding problem, which is similar but opposite of a memory stranding problem, wherein they've got low touch opportunistic pods that are backup jobs and log parsing and blah 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 that aren't important for day to day, but they get back pressure and then they have to run, and then it just has to happen. They don't actually need local DRAM. Like the latencies of a fabric attached DRAM are fine, and they just have these extra cores floating around. And with CXL, like you can just hawk purely fabric high latency DRAM to a few cores to run this backup job, this background process job that they have to run, and then get out, right? So like these are things that have value today, and these are those memory expansion and pooled memory examples. The shared memory example is what Rick was going into earlier, is the ability to put all of your consistency checking and log checking and like, did I actually write this data asset semantic network communication for a hard distributed database, not across like an Ethernet network where you have microsecond latencies or 100 microsecond latencies, but something where you have like tens or hundreds of nanosecond latency. And so without changing anything to those databases that have hard reliability guarantees, you get orders of magnitude speed up just by using this memory fabric. And so being able to schedule that and be confident that your resources are there is kind of a boon, right? It's one of the few things you get to throw money at still for computing. So
and again, apologies if this sounds like a silly question. I'm just trying to picture this in my head. So how this would work in practice. Are we talking about having like dedicated devices with lots of RAM in them connected to a switch, and then a bunch of servers can consume the RAM from that dedicated device?
That's exactly correct. So think
yes,
of the same way that NVMe OF or a JBOD or a JBOF works.
Right.
This would be, instead of JBOF, it's just a bunch of DRAM. And so you can have a slab of DRAM, and that slab can be a bunch of unique devices, or what we've also seen is discrete memory controllers that actually have DIMM slots on them that consume recycled or repurposed DDR4. So whenever people move to their DDR5 deployments, they'll have a lot of this CapEx that they've already spent in DDR4 that they can then just throw in DIMMs in a 2U memory sled. And then that memory sled will have, 100 to 200 nanosecond latencies instead of sub 20. But that's still an order of magnitude or more better than any persistent memory technology or flash-based storage.
Right.
Yeah.
Uh, and the difference between the pooled memory and the shared memory is that in the pooled memory, you carve out a chunk of memory and allocate it to a single server, but in the shared memory, the chunk of memory can be accessed simultaneously by multiple servers.
So think of this as the same way that
and
NUMA nodes work with a single
Right.
system. You can now have basically a NUMA interleave across the entire rack. Of
Right.
course, this is PCIe limited, so until we get magic technology that allows us to strap a whole AZ together, you won't be able to have core-to-core communications across AZ. But it is feasible right now with copper to get up to 4 meters, which is
like this.
plenty to get to 2 to 3 racks. So we can think of 2 to 3 racks wide, and you can have multiple memory shelves in rack 1, different failure domain than rack 3. So then you can do some type of interleave or even something like mem copy happening. So something, a lot of storage concepts are going to now start applying to memory, because we're going to be using memory in ways that we just haven't used it before, because we assumed like, okay, well, the system powers down and you lose memory. Well, now what happens when you can now actually keep the memory plugged in and replace your Gen 4 Xeon deployment with a Gen 6 Xeon deployment and never have to lose any of that memory at all, and just start operating it. Or you want to switch between ARM cores and x86 cores, you can do that by simply doing port-based routing, and saying, okay, we're going to put this on the low power cores right now, but whenever we really, really need to crunch away, we're going to put it on the x86 cores, or have a heterogeneous mix of those cores actually operating in tandem on the same memory region. So that's very exciting, but more the 2027, 2028 timeframe. In the near term, with Sierra Forest and Bergamo, we're having CXL 2.0 and switched topologies with real hardware-based switches should be available by Q4 of this year. And so hardware availability that is spec adherent will be here early 25 for actual purchase in production quantities. Sampling quantities probably late this year, which is why we want to have something to show, hey, you don't have to have some very special hard-coded, or only the hyperscalers can do this, because hyperscalers obviously are working on this behind the scenes on their own. We want this to kind of follow a lot of the parallels that Kubernetes did with CNCF, where sure, everybody can go write their own container orchestration, or we can all do it together. And by nature of doing it together, we accelerate adoption and make it more feasible across hardware vendors.
Okay. So, and again, just to summarize, so basically right now, nobody can buy this.
You can buy
Which-
memory expansion today. So in Granite Rapids and
Sapphire.
and Sapphire Rapids has 1.1, and I guess what's the current AMD platform
Burn.
have 1.1. And so you can put a type 3 memory device into those servers now. That, however, from a Kubernetes perspective, is relatively uninteresting, because that's just, okay, well, this worker node just has more DRAM now. There's no real need for orchestration across multiple system boundaries, right? You're still at a single system boundary.
Okay, but
Yeah.
so precisely, so for the pooled memory and the shared memory, though, the hardware isn't currently available, which is why you're
Not in
plugging your
production quantities.
orchestrator into a simulator to show how this works. I see.
Correct. Yeah, exactly.
Yes. Yeah. Yeah, everything's a little hard to get a hold of at the moment from that standpoint.
It does. The hardware exists. To be
Yeah.
clear, we're in QS, right? So we're in qualifying quantities and sampling. So this hardware does exist. We have put hands on it. We've run on real hardware. But if we wanted to have developers look at this, you can't just go to Intel and buy one of these processors, obviously. Or AMD, and you can't just readily go and get these switches on a normal PO. That will happen starting late Q4 this year, early Q1 next year. This hardware will be generally available for purchase in small scale quantities, and then scale up from there. Traditionally how your typical silicon life cycle goes.
Yeah, and like, as far as the, you may have heard from others that like CXL switching hardware is hard to get a hold of, which is true, because there haven't been a lot of vendors that have been doing it, simply because unless you had an FPGA or an ARM core or something like that you built, you couldn't really plug the CXL switch into anything, because the x86 platforms didn't support CXL 2.0, right? But with Broadcom, like, Broadcom knows how to ramp, right? Like, we don't have to argue about that. We know that Broadcom can ramp, and they've announced that they have samples of CXL switches, and we've seen those. And so they'll be ready for the 2.0 and the 3.0 ramp for the x86 side. So like it's coming, it's not there. And the layer, like the amount of code that doesn't exist to make this useful to something like Kubernetes or, virtual machines or whatever is staggering. I think
Right.
is
Yeah.
what
The
we're trying to
hardware.
communicate.
Yeah, the hardware will be there, and we've actually proven, not we, us, but we as an industry have already proven this. There's a company called Panmesia, that is in Korea, and they have an entire implementation of the 3.1 specification done in FPGAs. Right. So they have the entire thing done in FPGA. So it is proven possible and working. And there is silicon taped out for that from the various silicon vendors. It's just not available for consumption.
I just wanted to pick up on the software comment. Many years ago, I worked on a system called reflective memory that Oncle Computer made, which was essentially distributed memory across about 8 nodes.
Mhm.
The hardware worked well, and the software complexity, we were building mainframes and storage controllers with it. It's not to be underestimated. Even trivial things like upgrading the software where the data formats are different, or the fact that memory is persistent and memory leaks are persistent. The whole range of things. It is an immense challenge, I would say.
Yeah.
Yeah.
We're I don't know how else to say that.
Yes.
Um,
Bingo. Yeah.
I mean persistent memory is the very deep rat hole, right? I think that most people have settled on persistent memory is good for changing the refresh cycle of memory from not very long to maybe minutes, because that saves power. But still, we very much want to nuke it when the server reboots, because I don't want to think about persistent memory actually ever, unless it's in a storage context, right?
And so to be clear, there are other software vendors that are focusing on specific pieces of enabling CXL. And what we're specifically focused on, if I think the next slide is the software stack.
Yeah. So like, to be clear, the Linux community has made very large strides on the kernel modules and the drivers, right? And so from a single server standpoint, they're working very hard to be ready. And that's not to be like swept under the rug or anything like that. Like, they're doing a lot of work. It's just that the kernel community focus is on the node, not the nodes. And there aren't many people considering the plural. And the ones that are considering the plural have these sort of hobbled, they're demo ready proprietary things, which don't ever go very far historically, right? So we're looking at it from the standpoint,
Or their internal, behind a moat at very large hyperscalers. And right, they'll never see the light of day or be contributed back into the open, because they'll be seen as a differentiator for platform delivery.
Yeah. So we have an idea of like, we see sort of the ownership and the importance for the system shifting outside of the single node and more to the fabric itself, because over time the fabric will kind of become the boss of a collection of servers rather than the individual servers being the boss, right? So we see things going into the switch OS that runs on the fabric. We see the orchestration of configuring devices, getting device health, the various agents that need to run on the fabric and on the nodes, and how to interact with those things. Open most, as convenient as possible API and library, and then just making sure that everything works and is resilient is sort of the things that we see stacking up. So some things will run on the fabric, some things will run on the host, and depending on the device category, some things may run on the CXL devices themselves as well. together, you get a robust system that is familiar to the existing software platforms that we have today, so that you don't have a lot of disruption on that side. Most things can just continue business as usual when they see new resources, as opposed to rewriting large swaths of familiar software stacks is where we want to go with this.
Yeah.
So,
and so on the next page, you can see kind of a representation of how those discrete pieces fit into an actual architecture. So on the fabric, we'll embed in the fabric with a switch OS that'll provide more hardware abstraction and understanding what the orchestrator's intent is, and actually strapping together the various memory or type 1, type 2, type 3 devices to do what the fabric is asking. On the servers, on the host themselves, within the Linux kernel, we'll have an agent that essentially runs and takes those commands and intents and then translates those down to the fabric. And then in the application layer, we want to have either native commands that Kubernetes calls itself, or plugins that sit on top of those that translate those into those APIs and libraries. And so on the right side, you can see what we're targeting as a demonstration for the Open Compute Project Global Summit in October, and hopefully KubeCon in November. We think that would be a kind of a good 1-2 punch. And we would welcome any additional software players from an applications perspective that want to sit and leverage Kubernetes into this. So we want, we know that Uber and Meta both have said this is how we want to deploy and how we see the future of our Kubernetes deployments. And we want the orchestrator to be able to talk to the fabric and get the resources that it needs through a switch topology on essentially DRAM sleds. And that's really what we want to have for a demonstration in the October timeframe. So think of a quarter or half cab that would be all, you know, strapped together through a CXL switch or a CXL switch emulator, with memory devices at the bottom and then multiple servers at the top, and possibly, you know, a storage device flab in the middle there, so that you can have true disaggregated orchestration for your pod workloads in a cluster, right, scheduling real time by October.
I'm a little unclear as to what the next steps are going to be, and I'm kind of asking the question now in the interest of time, because we've only got a few minutes left.
yeah.
Sort of what is it that we're trying to do here? Because I can't see like a lot of developers jumping in on this or like contributing to this when, you know, it's so early and like hardware isn't available and that sort of thing. Like it's sort of I'm very excited by the concept of this, and you know, the idea of having an orchestrator provision memory to nodes dynamically based on usage is fantastic for sure. But it also feels like, you know, we're, you know, this is pre-alpha. It's very, very, very early from my perspective, in the sense that, you know, a developer can't reasonably interact with this other than maybe with a simulator. So there are very few like practical implementations we can do today.
Yeah, there's going to be no practical implementation until 2025. But the way that, so this isn't an optional silicon upgrade, is how I would put this. It's not here, it's not here, it's not here, but it's not like NVMe over Fabrics where you have to buy a SmartNIC and then you know, a fabric enabled flash shelf. This is it's not here, it's not here, it's not here, and everything you buy from now on, it is just baked in, right? So the transition mode between it not existing and it existing is kind of a very quick and painless transition from the hardware acquisition perspective. And what we're trying to fill in is the gap of, well, because the hardware exists now, people are going to want to dev on it, and then they're not going to be able to because there's no way to do it because you have to write your own memory fabric manager.
Yeah, so it does feel like there's a chicken and the egg problem from that standpoint. But so you said simulation, and I do need to correct that. I mean, it is emulation, not simulation. So
Okay.
QEMU is running all of the kernel code, right? And because QEMU wrote that Q35 PCIe pass-through layer forever ago, the CXL folks jumped on top of that, and basically, like, when you put this stuff together, if you had these devices and you plugged them into your QEMU VM, they would just start working. And so, like, anything that you wrote on top of that would not be like, and then magic happens and then you do the thing. Like, no, like, it's going through the full code path to get down to the device. It's just that presently, when it gets down to the device, it's a memory map file, right? But like the full path through the Linux kernel, it all talks CXL. It does all the PCIe register stuff. It does everything that it's supposed to be doing is supported in QEMU. It's just that it's not a switch. It's a collection of upstream and downstream Q35 emulated ports, right? So like right now, when we do this, and you can toss a software stack into it and everything like that, it's a nested QEMU image. Like, you launch a gigantic QEMU image, and then you launch a bunch of QEMU images inside that QEMU image, and they all connect over this PCI or this CXL switch fabric,
Okay.
right?
Yeah.
Okay. I
So,
get that.
yeah,
But,
yeah.
but my point is, I'm assuming the hardware vendors are not selling this and going, hey, buy this. Oh, but you can't use it until somebody develops software for it. Presumably, they're all working on some sort of fabric or some sort of like
We are working on the fabric with them.
Yeah.
I see.
So like,
Yeah.
Intel, AMD, that they have all deferred the fabric to us because it is not their business to. So if it was a fabric that was all for a single vendor, then it would be in their best interest to do this. Because it's a heterogeneous multi-vendor ecosystem, they have no interest in providing support for interoperability.
Okay, so you're providing the fabric that will work across multiple devices.
And vendors, and
Uh-huh.
all switches, so we will be hardware agnostic, similar to the way that Kubernetes is completely hardware agnostic.
Yeah. And so that's where at this point we're looking at it from the standpoint of to speed up the chicken and the egg problem. We need to start plumbing steel threads from application all the way down to hardware, even if the hardware is emulated. And we've looked at Kubernetes and the history of it. Some folks proposed a CMI to Kubernetes at the Linux Plumber conference, and everyone was very polite, but they also said no, right? In the way that we say no while being polite. And so, okay, so fine. So other discussions at companies have been like, well, I just want it to be more memory. Like, I don't care about the fabric or anything else like that. I want the worker nodes to just suddenly have more memory, and I can report that I have more memory. But you sort of, there are a bunch of challenges with that can be solved, but you lose some of the richness of, this is fabric attached memory, right? Like, you lose any sort of expectations of how robust is this, how low latency is, like, what's the performance, what's the latency, am I fault tolerant, like all of those sorts of things. When it just gets hawked into kernel memory, it's lost, right? Because by definition, the Linux kernel is DRAM, right? And so we're looking at it from the standpoint of, like, is this a plugin to CSI? Does the core of Kubernetes get extended to have more descriptors on memory beyond I need this much and I can't have less than this much, etc.
But CSI is more of a storage interface, right? It's not. It doesn't really
Yeah.
define. I mean,
So
Well, I
there
guess
is a
the semantics, the semantics here are pod awareness of far memory, or just Kubernetes cluster awareness, right? Do we want Kubernetes at a cluster level to just know that this resource is available and do what it needs to do to attach that memory to provision pods? Or do we want the pods to have the awareness and say, I specifically want far memory to be attached,
I mean,
because I don't have,
you know, like one obvious thing that's just popped into my mind now is this almost feels like it would be something you might want to integrate into like the container runtime, such that, you know, when you're spinning up a container and you're allocating, you know, memory to the C group's memory map, you're allocating it to a remote pool or something. Like I don't
correct.
know. It feels
So we threw a bunch of new information at you, and there's a
yeah.
bunch more too. So one of the things, for some types of memory, classes and pools of memory, people have proposed treating it like a block device, right? And this has been done before with Optane memory and stuff like that, because they sort of punted on it because Optane was never going to be as fast as DRAM. So rather than believe that it's DRAM, they treated it as just like high performance storage, right? But there's something called a DAX device for CXL where it gets rid of all virtual memory and TLB stuff, and it's just like a blob of memory that you can address however it is you want to address it. And once that DAX device existed, which wasn't a CXL thing, DAX existed beforehand, but CXL co-opted it. And then people started to put file systems on top of the DAX region, and it's just faster storage. And so when you have this concept of like memory that persists after the pod fails, do you treat that as a storage resource? Like, disregard the fact that it's DRAM. Do you treat that as a storage resource and like you can just move it and migrate it to a new pod or bolt it onto a different pod after something else has exited? Or do you treat it like another volume that you can add to a runtime in progress to just give it more resources, prevent it from an out of memory error, etc.? And so like that's where we're trying to sort out where this should plug in, because there's a bunch of different folks that have different ideas in Kubernetes about where something like this should exist. And we want to integrate
We want to
in a way
upstream
that,
this.
yeah, exactly. Yeah, I mean, we do. We don't want this to be a one-off or a novelty. We want this to be something that is
No, I get it.
accepted.
I get it.
Yeah.
But you know, just to be devil's advocate for a second, the statement you want to upstream this, this is fairly undefined. It's a group of ideas at this point, right? And it's hard to upstream something that you haven't, like it's not an idea that we need to upstream, right?
Yeah, the thing that we want to upstream is an API expressing need, right? So
Right.
it's something where like Kubernetes says, what have you got? And I need this, and I'm done with this. Like those three atomics can be very complicated quickly. But the point is like, I don't want to have to know what CXL is. Like I just want to get more stuff from you.
Yeah.
And the get more stuff and release stuff interface, we don't know
That intent
where
doesn't
that
exist in Kubernetes right now, right? The intent for the cluster scale to say, I just need more memory and it to be available is not that's not a concept that exists because we can't just on the fly add memory, right? You can add a new worker node, and then that comes with other resources attached to the memory, but you can't just add memory, right? That's a completely new concept. And so what we want to do is make sure that the way that we implement that is something that we
Has
can
legs.
upstream or
Yeah.
has a landing place, because having somebody run a special flavor of Kubernetes that enables pooled memory is just a non-starter. Right.
I mean,
Yeah.
look, at a very, very high level, it feels like you have like two groups of APIs, right? You know, from an orchestrator level, you need to be able to declaratively say, I have X amount of gigs of RAM that I need to map to this node. And then, you know, and that's almost a reservation rather than a mapping, because then you kind of want the runtime to be able to say, I'm spinning up a container, I'm going to use one of those 200 gig, and I'll connect it to the names, you know, the C group's namespace for this container, and it's going to run. So there's probably like, you know, it's not a simple API of um uh, sort of uh connect, add, delete. It's more like probably reserve, connect, attach, and free from the reservation, as opposed to, you know, and then, you know, there are lots of options available because, as you said, you know, since if it's a shared pool, or a pool which can be used across nodes, you then move into the scenario of, well, you know, if a node fails, do I just start up the pods on another node, and reconnect the memory and all of those kind of things? But we I think you kind of need to shape out a little bit as to what this is going to look like, and a certain amount of what this is going to look like, it depends a lot on what the actual products and capabilities actually look like at the end of the day, right? This is not um you know, it feels a little bit like developing the software to use hardware that doesn't exist yet is quite a tough ask. Especially
Yeah, it's pretty challenging.
Yeah.
Which is why, but yeah, but
Can
the we
I ask just a question here? Because what I
Yeah.
didn't hear is kind of that first step out of the door, which is a container spec had, or a pod spec has containers that have resources, and resource have request memories and limit memories. And right now, there's only one flavor of memory in there.
Right.
Right. So the first step in my mind, it would be how to have more than one flavor of memory in a container resource request and limit. Right? That to me seems actionable and doable, but it will exercise that whole path down, at least in the extension mode. We haven't gotten to pooling or anything complicated yet, but at least taking that first step. And so that you don't need a fabric manager or anything there. You just need to solve the different flavors of memory. So is that something you're doing, or are you waiting
Yeah.
for somebody else to do that?
So we
Well,
will do that. We want guidance on the direction to go that will not cause heartburn when we do that.
Right.
Because I think just doing it and implementing it and then saying, "Ha, we did it," and then presenting it, like that is obviously, from what we described here, only one facet of what we're working on, and we're not a team of 300 engineers. So like we can't really afford to have much throwaway work this early.
Yeah.
Yeah.
I hear that. That's your that's your choice. of what you're going to engage in and how much you're going to swing for the fence. But if it as a deployment, you can't make it more complicated for deployment to start, right? And so being
Correct.
able to consume and have the request of any memory or a class of memory is at least now allowing a deployment to decide if they have this hardware infrastructure, how to use it without changing anything other than their container spec.
Right. And that was one of the things that I was actually thinking would be one of the nicer places to start, is just saying like, look, when I present my manifest for what are my needs as a pod, like I can run on this lower tier, like this lower performance tier. Like that's fine for me as long as I have this much, right? Like those
Yeah.
sorts of descriptors seem to make sense. It's just honestly, it's core, and I didn't know if like coming in and being like, hey, I want to add these new descriptors to the very core of how Kubernetes requests resources was going to fly.
Yeah, like
Well,
that seems problematic. Yeah.
But to be fair, like, and again, sort of, I want to bring this back to this, right? Like, and correct me if I'm not correct, Tom, but like, I don't think we're talking about Kubernetes yet. Like, we're talking about the runtime, the container runtime. Like, this is a way. The first step is, how do you integrate this into a container runtime?
Yep, you're right. The orchestrator, when you're describing a pod, is basically setting that discussion with the container that's getting spun up. Yeah, you're right, Alex. And I was also going to up level it, as say, I think you got to talk memory first before we get too far much before we get into a storage discussion. I can see how once you have more future allocation requests, things that might be data object based, that we should have a follow-on discussion when we start sharing and moving and replicating and doing all the DR kind of stuff. But to me, that's miles away from the first step that we'd have to take. And I think it's a little, the trail isn't clear yet, and you got to take that first step. That's just my opinion. I think we're too early on the storage discussion side.
And we very much appreciate that feedback.
Yeah.
I mean, is there, as far as like another call that we should be joining, like who are some folks that we should go talk to next? Because we are just starting to probe from this standpoint.
So one of the things I'd recommend is I can ping a couple of the guys in the runtime tag, and maybe do some introductions, because I'd suggest you have a word with them, similar sort of thing, with a focus, however, of how do we get this integrated into a runtime, and then maybe get people, say, from the Containerd project or whatever or the cryo project from to engage, and see what the right way of doing that is. But it kind of feels like you need to get into a runtime first before you can consider then how you orchestrate it. This needs to go into a runtime standard, I think, because it's how does the runtime connect to the memory? It's the runtime that's going to do that abstraction, not the orchestrator.
Well, I think there's two ways to look at it, and I think that's one way to look at it, and that's the second way that I talked about, where the pod actually
I tell you what, unfortunately,
we've got to, we're over time.
Yeah, we're way over. We appreciate that.
Yeah.
Sorry about that.
I'll ping the Tag Runtime group and have one of them reach out and do some intros as well, and then we can take it from that next step. But also happy to have, you know, further conversation in another tag call here too.
That's great. Yeah, because like I said, we're not only just what the interface looks like, but like how much Kubernetes wants to get in, like how much Kubernetes wants to know about the underlying hardware architecture and connections also is important to understand. Because they could, like, you go whole hog, or you could be like, I just need stuff. Like, just give me the things and tell me when they're ready, and then I'll do stuff with it. Like that
Right.
layer of abstraction is also something that we want to learn, because it could go either way. Like there's
Yeah.
a bunch of ways
Yeah.
to do this, and we want to do it the way that the community is happy about, right?
I'm not sure you know your community yet. That was the other thing I wanted to say is the number of people that are going to dive into this complexity and deal with it in a world that wants automation and don't bother me is very challenging, because your claim to fame is trying to recoup stranded memory and stranded CPU at the beginning of this life cycle. The pooling has new architecture, but that has all bunch of changes and different winners and losers who are going to win. And you haven't presented that a chart or anything that says you need to have a million cores before this is going to be worth your while to try to optimize their use, or 100,000 or 10,000. You got to, you know, there's got to be somewhere that your problem has to be big enough that you have wasted enough money on stranded CPU and memory to go after this with complexity. And I don't think you've defined that yet. Not to say it isn't there. I'm just saying your community is going to look at that and say, hey, I'm spinning up Kubernetes in an automated factory. I'm not going to mess with this crap. And then you're going to have other people that say, I'm running a bank. This is cool. I can get the best trading numbers. You know, I want this all in, you know, so your community is going to affect deployment, and deployment affects scale, and you gotta wrestle those. So I'm done.
Yeah.
Anything else, Alex?
No. I think that was good advice. Unfortunately, I do need to drop.
Yeah,
because
we got it. Yeah.
Yeah, no, we appreciate the
Thank-
time,
yeah,
and we
thank
look
you
forward
so
to
much
that
for the
email.
time.
Thank you.
Thanks, everyone.
Hi, guys.